Good morning, Hebden Royd. A pleasure to be here to give you a talk which I've titled rather cryptically 277, because what I'm describing is the design and the construction of a telescope that was designed in the 1930s and built in the 1940s. Telescopes are defined by the size of the lens or the mirror that collects the light, and in this case I'm talking about a telescope with a mirror 200 inches or 5 meters in diameter, and it's been operating for the last 77 years. Hence, a 200-inch telescope that's been operating for 77 years old. It's now effectively 77 years of age, hence 200 at 77. So I appreciate that you're not astronomers, but you might still appreciate the engineering behind how you build the world's largest telescope well over a century ago. Sorry, approximately a century ago. I got interested in astronomy as a lad when I looked in books and saw images like this. This is a nebula, a large cloud of hydrogen out there somewhere in the universe. And I looked at images like this in books and I thought, wow, the universe is an amazing place. I wonder how things like this come to be. And how do we study things like this? Why does it look like a chess piece of a horse head? And how long has it been there? How long will it survive? What's it made of, etc.? This piqued my interest in the universe. More so than any other image, this got me started. So what I'm talking about is effectively the world's largest telescope when I was going through my schooling. And it was built by this man, George Ellery Hale. I haven't got time to tell you all about this man, but he built the world's largest telescope, not once, twice, three, 4 times he went through and built ever larger telescopes so that we could see further into the universe. I'll be talking about building the 200-inch telescope, how you decide where to put it, how you make a mirror that's 5 meters in diameter, and how you make the telescope itself to effectively point this mirror so that you can image the stars, planets, galaxies, whatever it is you're interested in. How can you point this telescope accurately on the sky? And finally, I'll be saying a little bit about how it's going still 77 years later. And then I'll acknowledge the various sources that I got the information from. So this is the man, George Ellery Hale. A famous astronomer in his own right, but in a sense, his work on astronomy has been overshadowed by the fact that he has been a fantastic organizer and a designer of telescopes and an organizer of getting them funded and built and operational. So he's had the vision and the drive to actually make the world's largest telescopes. So I'm not going to go through all of his achievements, but it started back in the early 1900s when he was the director of the Yerkes Observatory and oversaw the building of the Yerkes refractor. This is a lens 1 meter in diameter, effectively the largest refracting telescope, the largest telescope with a lens at the front end. After that, telescopes tended to be built with mirrors because it's easier to build large mirrors than it is to build large lenses. So then he oversaw, as the director of the Mount Wilson Observatory, the building of a telescope with a 60-inch mirror, and then after that a 100-inch mirror, and that was operational in 1918. Generally speaking, when you start thinking about building the largest of anything, telescopes are defined by the diameter of the mirror, and what tends to happen is you tend to go up an extra factor of 1.5. So you can see from 40-inch to 60-inch, from 60-inch to 100-inch. If you go from 60 inches to 100 inches, it's half as much again on the diameter. It means the collecting area of the mirror is roughly doubled. So you can see fainter objects, and with larger mirrors, you can see more precise detail in those objects. So there's always a desire to always go to larger and larger telescopes. And even as soon as the Hooker telescope, so called because it was funded by a business magnate called Hooker, No sooner was that built that Hale started to say, well, it's great to have a collecting area of 100 inches, but why don't we think even bigger? And instead of thinking half as big again, let's build a telescope with a 150-inch mirror, he thought, why not go all the way and think about something that's 200 inches, twice the diameter, 4 times the collecting area. This will be a huge move forward in telescopes being able to collect faint light from distant objects, as well as seeing detail in distant objects, such as, for instance, the distant galaxies which were being discovered at the time. Hale always thought, let's get more light, and more light always means a bigger mirror. How do you get something like this funded? Well, George Hale was a bit of a billionaire whisperer. He knew who to talk to. And ultimately, in the 1920s, he went to the Rockefeller Foundation and he managed to convince them to put up the entire budget of $6 million, quite a lot of money back in the 1920s. This is the entire budget, not only for the telescope, but the telescope in its observatory dome and the entire infrastructure of the observatory site itself was all funded by the Rockefeller Foundation. So Hale was amazingly successful at getting them to put the money on the table and effectively putting all the money down rather than part funding and letting somebody else come up with the difference. So having got the funding from the Rockefeller Foundation, where are you going to put the world's largest telescope? Well, these days, the world's largest telescopes tend to be on volcanic islands like Hawaii or the Canary Islands, or possibly the high deserts of the Atacama Desert in Chile. But back then, the preferred site was Hale and his colleagues were centered around California, in particular Los Angeles. So they said, well, how close can we get to Los Angeles? This is the area. This is Los Angeles itself, with the island of Catalina just off the coast. Los Angeles, even then, was getting rather large, and the Mount Wilson Observatory, which was the observatory for the largest telescopes at the time, was sited just to the north of Los Angeles. And you can perhaps appreciate that if you have a big city that's growing with a lot of lights, because you've got a few million people living there, that's not the best place to find a nice dark sky so you can observe the universe. You really want to avoid population. And Los Angeles was growing, and then there was San Fernando and San Bernardino. So the original Mount Wilson Observatory was getting surrounded by millions of people all wanting to illuminate their streets, and therefore Mount Wilson was looking like not the best place to put the new generation of telescope. So Hale said, let's send out a few scouting parties to the regions around California to see if we can find a mountain top with a nice dark view of the sky. So he sent out a few scouting parties. A few possibilities were found in the mountains of California. They checked whether or not these were good places for nice dark skies. He also had the prescience to actually check with his colleagues in California Institute of Technology and ask them, geologically speaking, is this a good place to put a telescope? And the professor of geology there at the time, one certain Richter, said, yes, he of the Richter scale, said, putting a telescope on the San Andreas Fault, not a good idea. However, if you decide to put it in one of your sites, Palomar Mountain appears to be a chunk of granite, which is something like 30 miles long, 10 miles wide, and at least 20 miles deep. It is a few trillion tons of granite. So even if California has an earthquake, it wouldn't go far if you bolt your telescope mounting onto that mountain. So it was decided that Palomar Mountain would be the best place to put this telescope. Yes, there is a little bit of a village to the south there called San Diego, and that got a little bit larger over the years, but it wasn't as close and it wasn't as big as Los Angeles. And so although it does produce a little bit of light pollution on the southern horizon, that's not too bad. So Palomar was decided that's where we're going to build this. That's what Palomar Mountain looks like now, or at least a few years ago. I visited it on a beautiful day back in May 1982. It looks like I've changed my shirt since then, which is excellent. But yeah, as a student, my hair was probably a little bit longer. So that's what it looked like. And at the time, it was definitely shirt sleeves weather, and it's difficult to appreciate that because of its altitude, it's sitting on top of a mountain, 6,000 feet or 1,700 meters or so, that during winter, it does actually get quite cold up there. So you actually have to pay people to shovel snow off the top of the dome, otherwise the dome collects hundreds of tons of snow during the winter. And it's also not the most accessible. If you want an observatory with nice dark skies, you need to get away from people. And if you're getting away from people, you often get away from infrastructure as well. So they had a rather difficult road to take all the material they needed up to the top, the so-called South Grade, in order to get everything they needed, because this is effectively a virgin mountaintop. There's no infrastructure there. They had to take up everything they needed, all of the material they needed to make the buildings, to make the observatory, to make the telescope. Everything had to be taken up this rather windy road to get to the top there. If this is going to be the world's largest telescope, how are you going to actually mount it in such a way that you can point it precisely where you want? This story of the 200-inch telescope is a story about a huge piece of engineering which is made to very high precision, because you want to be able to point it very accurately with an angular error of only arc seconds. If you think of 1 degree, you know what 1 degree looks like on a protractor, divide that into 60 arc minutes and divide each of those arc minutes into 60 arc seconds, you can see that 1 arc second is 1 over 3,600th of a degree. It is a tiny, tiny fraction, but they wanted to be able to point this telescope accurately with arc second accuracy to any point on the sky, and as the Earth rotates, follow those objects, regardless of whether they're stars, planets, or distant galaxies. So how are you going to mount it in order to keep this, what ultimately will be a fairly large and massive telescope? How do you get it pointing in the right direction? Well, amateurs know that there's quite a few ways that you could, in principle, mount a telescope in such a way that you can follow the stars as the Earth rotates. We're not going to go through all the details, but there's 3 different types of mounting, so-called German fork and English mounting. Here you have a counterweight to balance the weight of the telescope to make sure the telescope can move smoothly. In this case, it's a fork mounting, and if your telescope is very massive, then there's a possibility that this fork might flex slightly, and so supporting it top and bottom gives you a lot more rigidity when you have a very massive structure. So the English, or the so-called yoke mounting, is preferable when you've got a lot of mass to move. As it happens, the 3 previous telescopes that Hale was involved in constructing each had this various type of mounting. So the first one, the Yerkes, had a big counterweight on the side. The second one, the 60-inch at Mount Wilson, it doesn't look like a fork mounting because it's a very squat structure, but that is a fork. And for the 100-inch, they used this idea of the English yoke, supported on both sides and with a south and a north bearing. But there's a number of limitations of having a yoke mount. Yes, it's very sturdy, but you can't point this telescope in the direction of the Earth's axis. This angle here that you can see indicated by the dotted lines, this is the axis of the Earth. So as the Earth rotates, the sky appears to rotate around that axis, the so-called polar axis. But if you have a yoke either side of the polar axis, it means your telescope can't point in that direction because it fouls the bearing itself. And even if you made the yoke larger, you would still be looking at the bearing, not looking at the sky. So there's a limitation with that particular type of mounting. And Hale said, well, I want to build the world's largest telescope. This will probably be the largest, it will be the largest one ever made, and it will probably be the largest telescope I build before I die. I want this telescope to be as close to perfect as possible. I don't want it to have the same limitations as the 100-inch that is now operating and has been since the 1920s. And in particular, the 2 limitations was, one, the mounting that I've just mentioned, the yoke mounting, where you can't look at the North Celestial Pole, the point on the sky pointed to by the Earth's axis. But also he wanted to get around the limitations of the glass that was used to make the mirror of the 100-inch telescope. It was made of plate glass. And plate glass expands and contracts as the temperature goes up and down. And if you're trying to make a curved surface to focus light, the last thing you want is for your mirror to change shape as it warms up and cools down. And you can't always predict what the nighttime temperature is going to be. You can have a weather forecast, but you could be wrong by a couple of degrees, in which case the mirror would then take time to cool down until it contracted and then hopefully regained the correct shape. And while it was cooling down, it wouldn't necessarily have the right shape and you wouldn't be able to use the telescope. And in the case of the 100-inch telescope, it might be that on a particularly warm or particularly cool night, it might be unusable for hours, maybe even half the night, whilst you waited for the temperature of the mirror to come to equilibrium with the nighttime temperature. So that's a problem with plate glass, and Hale figured that we have to get around that problem. So firstly, getting around the problem of the fact that with the yoke mounting, you can't point the telescope in the direction of the polar axis. How did he get around that? Well, he went for this rather iconic design of a yoke mounting big tubular steel either side of the telescope truss with the mirror at the bottom there, but an enormous horseshoe at one end. And with the horseshoe at the north end being supported on oil pad bearings, it meant that the telescope, if you wish, can point directly along that axis because it simply nestles in the gap made by the horseshoe. So it's not there for a design aesthetic, it's there for a good reason. It enables you to point the telescope essentially anywhere in the sky. The second problem was this plate glass mirror. If we have a look at the Hooker mirror, this is looking into the side of the mirror. The mirror of the Hooker telescope, 100 inches in diameter and rather less, about a foot thick, something like that. And this is looking into the glass. The front surface of the glass is usually coated with silver or aluminium to give us a nice reflective surface. But here you can see the glass itself. Well, it's been poured in various chunks and part of the glass has solidified before the next chunk of glass was poured in from the melt. And that gives you A, lots of layers, and B, thousands upon thousands of air bubbles. And that means, again, if you want to get the temperature right and let it cool down or warm up, different parts of the mirror are going to expand and contract at different rates depending on how many air bubbles it's got in it. So the mirror surface will distort as it warms up and cools down. Not ideal. So the question is, what can you do? Can you simply scale up the 100-inch mirror and make a 200-inch mirror? It's going to be twice the diameter, so it's going to be 4 times the area. It'll have to be thicker, which means it's going to be 8 times the mass. The original Hooker mirror was 5 tons of glass. So do you really want a 40-ton mirror that you're trying to point accurately around the sky? Well, using plate glass, you'd have these horrible distortions, and they would be even worse than with the 100-inch simply because it was so much larger and so much heavier. So they decided to go not with plate glass, but to go with a low expansion glass. These days we would call them borosilicate glasses, or everybody else calls it Pyrex. That's the trade name for the Corning Glass Works. Pyrex you can take from the oven and put it under a cold tap because as it heats up and cools down, it doesn't expand and contract anything like as much as plate glass does. And therefore, it's ideal for making mirrors because even if you've got the temperature wrong by a degree or 2, it basically will not change shape as it warms up and cools down. So to avoid having a mirror 8 times heavier, despite scaling up by a factor of 2 on the diameter and on the thickness, they decided to come up with some innovative ways of making mirrors. So how do you make a mirror? You start with molten glass, and ideally you want a pancake. The mirrors are round and you want a glass surface which you're going to grind to the right shape to make you the focusing surface that will allow you to focus on whatever object you're interested in. So normally you will have a mold which is pancake shaped and you will pour molten glass into the mold until it fills up, and then you have your pancake. You would then let it cool down. But remember, glass will contract as it cools down. It might be 1,500 Celsius when it's there as molten glass. You want to get it down to room temperature, but you don't want to cool it down too quickly, otherwise you'll introduce stresses as the whole thing tries to contract. And of course it will lose heat from the outside, but any heat on the inside, you need to give it time for that heat to slowly drain away and transfer to the surface and then radiate away. So for the mirror that size, it might take months to cool down from 1500 Celsius down to room temperature. If you simply scale up to 200 inch, they calculated that if we simply scale it up, it wouldn't take months to cool down. We'd have to cool it so slowly to make sure there were no stresses in the glass. It might take a decade to cool down from 1500 Celsius to room temperature. That was unacceptable. So after cooling down, they figured that, yeah, we can then grind the surface and coat it with a thin film of metal to give us a nice reflective surface. But we've got to figure out a way of cooling it down quickly. We can't wait years for it to cool down. So they went with this idea of trying to reduce the mass, improve the stiffness and reduce the mass to allow it to cool faster by introducing into the mold fire bricks or cores. And then you pour the glass in and the glass flows around those fire bricks. You still have to worry about cooling it down slowly, but no longer over decades. Now you can cool it down in less than a year. Once it has cooled down, you can then take the fire bricks out and you're left with a front surface, which again, you grind down to the right shape. You might remove quite a few tons of glass to do that, and then you coat it with metal to give you the right shape. So if you do this, if you put fire bricks in your mold before you pour the molten glass in, then you end up with the front surface, which is just like before. It is the shape you want to focus the light in the telescope, but you now have a ribbed back because you've got lots of air gaps effectively where you used to have these fire bricks where the glass has flowed around the fire bricks. So that's what the mold looks like. 5 meters in diameter, full of these rather rounded looking fire bricks. Some of them are different shapes. We'll see the shapes more clearly in just a moment. A large plug in the middle because we want a hole in the middle of the mirror, which I'll come back to shortly. So I appreciate you can't see all the detail in this. This is an overview of the Corning Glassworks. Hale went to Corning, said, can you make us a Pyrex mirror? They were making millions of custard jugs, so they figured, yeah, if we can make custard jugs, we should be able to make you a 5 meter diameter mirror. So again, you can't see the detail, but that's where the mold is. That's where they are going to pour the molten glass. And they carry the molten glass around in these huge ladles that look like ice cream scoops, with teams of people carrying them from a large tank of molten glass into the mold where they pour with expert eye. They decide where they're going to pour the glass to make sure the glass flows around these fire bricks. So let's see that in action. Is it possible to have the lights off? That might be a little clearer. So here we see the team there putting an ice cream scoop into the molten glass. Water is sprayed onto the ladle to make sure the ladle doesn't melt. And we can see it from a slightly different angle. There goes the ladle into the tank. It is then turned and scoops up something like 100 kilograms of molten glass, which then comes out. They scrape away the molten glass, the excess. Again, they need water to be played onto the ladle to make sure the ladle doesn't get too hot. And then the ladle is taken over to the mold where the glass is then poured at the relevant place into the mold. Any excess glass that doesn't come out of the ladle at that point, they return the ladle back to the outside of the oven, turn it upside down. Excess glass is dumped into a wheelbarrow, and then the wheelbarrow is taken back to the glass tank where it is effectively recycled. So that's how they actually take the glass from the tank to the mold. 100 or so kilograms at a time, with a whole load of people at this end to counterbalance the weight. Most of the weight is taken by this overhead track. The guy at the front there has got this face mask, which he's holding onto with his teeth in order to look through and be able to see what he's doing, even though he's looking into a furnace effectively at about 1,500 Celsius or so. So here they are actually pouring the glass into the mold. I assume the guy on the left, he must be a supervisor because he's wearing a hat. So he's presumably checking that everything is going okay. You can see that the ovens themselves are basically made with fire bricks, and they are fired with electrical heaters to make sure that they stay warm, and that heating is then gradually pulled down after all of the glass is in place to bring it down to room temperature. But unfortunately, the first time they tried this, which was 1934, the ovens themselves, which are made from bricks, some of the bricks on the inside were a little bit more loose than they appreciated, and some of those bricks actually fell into the molten glass. And that produced a whole load of gouges in the final mirror blank. They were wondering whether or not they could get away with that, depending on how deep these gouges are. Remember, they're going to be grinding that front surface down to a curve to allow it to focus light, but unfortunately these gouges were just too deep, and so they decided this particular casting would not work. So they took the experience and said, right, we are going to make absolutely sure all of the fire bricks on the inside of the oven are absolutely fixed. Also, they had a problem with some of these cores that are supposed to be giving you air gaps for the glass to flow around. Some of those dislodged and floated to the surface as well. But finally, a year later in 1935, they got it right. The second casting basically worked as intended. And now you can see, after a year or so of cooling it down, they finally had a mirror, and now you can see more clearly the ribbed structure. Now that those cores have been removed, you're left with this rib structure, which makes the mirror much stronger because of the ribbing, but also much lighter because of all of the glass that's been removed. Here, they are simply testing with the light, shining through the glass to make sure there were no stress fractures in any of the glass. This is simply a promotional picture. There's no point in measuring after you've done that, because if it's wrong, it's wrong. But basically, this is the large hole in the middle of the mirror, gives you an idea of scale. The 5 meter or 200-inch diameter has something like a 1 meter gap in the middle there. Again, you see very clearly the rib structure. You see some of them are simply large hexagonal voids to reduce the mass. Some of them are circular. Those are designed to take the mirror support system. You have to make sure that when a mirror is supported from behind, remember it's quite a few tons, this mirror. It's going to end up as something like 15 tons of glass. You've got to support this very carefully to make sure this glass doesn't sag in any way whatsoever. If you want the shape of the mirror to stay accurate, regardless of whether you're pointing your telescope up or whether you're pointing your telescope towards the horizon, you have to be absolutely sure that you're supporting the mirror in such a way that the mirror itself does not flex. That is an engineering marvel in itself, which I haven't got time to cover, but it's in one of the drawings on the front table there. So Corning wanted to say in their adverts that, yes, we normally make custard jugs, but in this case, we've actually made a 200-inch diameter mirror. For some reason, they always called this the eye. With lenses, you might understand that, why you would call a mirror an eye, but this, when you're talking about large telescopes, the public seemed to think that a large telescope was an eye on the universe. So they talked about an eye that sees that many miles. Why did they choose that number? Well, they were hoping that this telescope, when it was built, would be able to see 1 billion light years. In other words, they would be able to see galaxies at a distance such that even at the speed of light, the light from these galaxies would take 1 billion years to reach us. And if you calculate 1 billion light years in miles, that's the number you end up with. So that's why they said this telescope will be able to see that many miles. They had problems with the second casting. It was not disastrous, but they did have still problems with the annealing ovens. They had a flood of the nearby river. The annealing ovens were powered by transformers taking power from the grid. And remember, we want to slowly take that temperature down day by day by day over the course of a year or so to eventually get to room temperature. But they had a flood of the neighbouring river, which was going to hit the transformers that were feeding power to the annealing ovens. So they had a real problem deciding, what are we going to do? Are we going to let the water hit the transformers, or are we going to turn the power off and risk introducing stresses into the glass of the mirror? In the end, they found innovative ways of dealing with that as well. This is the mirror. Once it was finished in Corning, it was sent over to California. Again, you get a nice idea of the structure on the back. The entire 20-ton mirror is on a strap there. I'm not sure I'd trust that, but it seemed to work okay. Again, this looks translucent. You don't even notice the front surface because all you see is the ribbing on the back surface, regardless of which way you're looking at this structure. When it finally arrived in California, they said, right, we now have a blank. What we want to do now is to grind it such that it's the right shape. A parabola is the perfect shape for focusing light from a distant object. So what we need to do is to get a team of engineers, a team of technicians to grind the front surface of the mirror to the right shape. It took 21 men 11 years to do that. Now, 11 years is longer than it should take. It should only take a few years, and the reason it took 11 years will become clear in just a moment. But yes, it took a team of people a long time to do this. The mirror was placed on a huge turntable, and then a grinding tool moved backwards and forwards as the mirror circulated to make sure the grinding tool covered the entire surface and eventually produced the right shape. How do you know when you've got the right shape? Well, you can calculate roughly what it needs to be just from the mechanics. But in terms of getting it accurate, and remember, in order for a telescope to produce nice, crisp images, the accuracy of the surface that you generate needs to be better than the wavelength of light. And the wavelength of light is just a fraction of a micron. It's basically small enough such that if you're off by more than a few millionths of an inch, you will not get a perfect image. So how do you make sure that you're grinding this thing to the right shape? Well, the mirror is ground when it's in that shape, pointing upwards, but it's tested by turning it through 90 degrees and then with the length of the laboratory using a test to actually make sure where does the light get focused from this mirror. Again, it's absolutely important. If you're grinding it in one position and testing it in another position, you have to be absolutely sure that that mirror isn't slumping and isn't distorting because of its own weight. It started out at something like 20 tons. By the time they had ground down a few tons of glass dust, it ended up as about 15 tons, but that's still pretty heavy. You have to make sure that you support it such that the test is an accurate indication of what's going on there. I find it very odd that these people seem to have pipes in their mouths. I can't believe they allowed tobacco smoke in a clean room like this. I wonder whether or not they're just an affectation, that they're so used to smoking, if they haven't got a pipe in their mouth, they don't feel right. So regardless of whether they're full of tobacco or not, you still see this occasionally. And no, that's not a Hoover down the bottom. That's a little electromagnet to pick up any tiny shards of metal that might be around to make sure they don't scratch the surface of the mirror. So the mirror was tested by a so-called knife edge test. That means shining light onto the mirror and looking at its reflection. And that's what that guy is doing there. And that allows you to actually tell whether or not the mirror is perfect to within a fraction of the wavelength of light. It's not an absolutely perfect test, but it's a very good way of telling that you're very close to the final figure that you want for the surface of the mirror. Whilst the mirror was being ground to the right shape, they started constructing the observatory itself on the top of Palomar Mountain. Remember, a big chunk of granite, so all they needed to do was effectively drill some piles into the granite, and that allowed them to start building the observatory itself. As soon as they got to the point at which they wanted the dome, remember, the dome has to rotate to allow the telescope to see any chunk of sky. So the walls are not particularly high, but once they started on the dome, they needed to have a track on which the dome could rotate. And here's the dome tracks being ground to precision. The engineers said to Hale, well, how accurate do you want these rails on which the dome moves? to which Hale replied, "1/1000th of an inch should be enough." So here they are checking that these rails are flat and accurately positioned. The intention is that once the dome is in position, the dome will rotate and will not produce any vibration of the telescope. That's the intention. So even though the dome is 1,000 tons, they wanted it with the precision such that when rotating, the telescope didn't even know the dome was rotating. No vibration would cause them to interrupt their observations. So there it is, the track is now finished, and now you can start to build the dome itself. This is 1937, and by the time the dome is getting close to being of the right shape, it starts to look like an astronomical observatory. This is one of the drawings that I've got on the front bench here. These are drawings by this technical artist, Russell Porter, who produced technical drawings of amazing complexity and somewhat amazing beauty as well. So this is a drawing he made in 1938. He had the ability to look at technical drawings of what the telescope was going to be like. He could envisage it in 3 dimensions, and in his head, he could produce cutaways of what it would look like if you removed this and exposed this underlying. So this effectively is a slice through the entire observatory, a slice through the dome, and a slice through the 200-inch telescope itself. And this is a useful one to sort of tell us a little bit about the telescope. So let me blow it up a little bit so you can see it. So this is a slice through the telescope. There's the telescope itself, sitting in this large horseshoe at this end, yoke here. And so that diagonal line there is pointing where the Earth's axis is pointing. So the telescope rotates on that axis to follow the sky as the Earth rotates. If we just make that a little bit fainter to make it clearer, the mirror itself is down this bottom end there. So there's our 5-meter or 200-inch diameter mirror. And if we were imagining looking at a star at the zenith directly overhead, the light would hit that mirror, and because of the curve that we've been talking about, the parabolic shape, it would come to a focus at the top end of the telescope there. And if you wish, an observer can sit at that top end. The telescope is large enough that the observer can ride inside the telescope. This was the first telescope that was large enough to actually allow that, to allow an astronomer to be on board if they wanted to be. So they weren't simply eyeballing through an eyepiece. Generally speaking, they were taking photographs with a photographic plate at the top here. And if you wanted a relatively wide-angle view of the sky, you would bring the light to a focus there and place a photographic plate where that observer is sitting. But for many situations, they wanted longer focal lengths because they wanted higher magnifications. This wasn't really a telescope built to take nice, pretty pictures of the sky. They wanted to look in detail at a particular star or a particular nebula or a particular galaxy. So they wanted longer focal lengths. So this was designed with extra mirrors underneath where the observer might sit for prime focus. There were a whole set of fold-down mirrors, so a secondary mirror could be placed there. The observer would not sit in that cage. The light would then hit the primary mirror, then the secondary, and then go through a hole in the main mirror. That's why the mirror had a hole in the middle, so that you could, if you wish, let the light through, and then you could have a whole load of instruments down there. It's a much longer focal length. You can see it's folded like this. It gives you a nice long focal length, nice high magnification of small objects. And it also has the advantage that because of the way it's designed, you can put quite a lot of instrumentation down here. You could put over a ton of instruments on the bottom of the telescope and it wouldn't unbalance it severely. And depending on what you were wanting to observe, there is a third option, and that is you put a third mirror at the intersection of the axes of rotation of the telescope, so the light hits the primary mirror, then the secondary mirror, then the tertiary mirror, and gets sent off down here. The advantage of this is, again, a much longer focal length, but one of the great advantages is that point never moves. Regardless of where your telescope is pointing in the sky, no matter what it's doing, that focus is always at a fixed point there in the basement. that means you're going to have extremely sophisticated or extremely heavy instruments. It doesn't matter how many tons they are, because that point doesn't move. And if you want to, you can shine the light down here and you can have a very complex spectroscope, for instance, to split the light into its component colors. And there again is a picture of an astronomer picking up the light as it comes down from that particular focus. The name there, coude focus, is just French for elbow, because of that elbow reflection in the middle of the telescope there. This gives you an idea of how it was constructed. Whilst the building was going on, while the mirror was being ground, the telescope itself was being constructed by Westinghouse. And this gives you an idea of the base ring of the telescope by how many people could stand inside it. This is the ring that ultimately would support the so-called mirror cell that holds the mirror itself. This gives you an idea of some of the bits and pieces that were made by Westinghouse. We can look at some of the detail. This is parts of the tube assembly were put together in Westinghouse. Ultimately, they made sure everything fitted together and then dismantled it to send it over from the East Coast to the West Coast for California. In the audience here is a certain Professor Einstein. He's a theorist. He's not interested in observing, but he is interested in, will this telescope be able to see galaxies in the distance that will actually confirm the general theory of relativity that he came up with a few years earlier. So he's definitely interested in observations as to whether or not they would confirm his theories. It's an apocryphal story, but it's a nice story. Mrs. Einstein was there as well. And somebody asked, or Mrs. Einstein asked, well, why should you build a telescope this big? And somebody answered her, well, Mrs. Einstein, the idea of building a big telescope like this is we can look out into the universe, we can see very distant galaxies, and we can work out whether or not the universe is expanding or not, and we can get an idea of the large-scale structure and the evolution of the entire universe. Mrs. Einstein said, so what? My husband can do that on the back of an envelope. Maybe that's true, maybe that's not. You get an idea of some of the structures here. This is part of the horseshoe that's being made. The sheet steel here on the outside and on the inside is about 4 inches thick, and these pieces of steel were bent to shape in a 12,000-ton forge press. So there's a lot of structure inside, again, to stop these things flexing. Yes, they have to be big and heavy because they're basically trying to point more than 100 tons of telescope into a point in the sky, but it has to be done with extreme precision. So you don't want too much flexure of, for instance, the parts of the horseshoe. That's another part of the horseshoe. Again, it's probably a publicity shot, because what's the point of measuring? It's too late now, it's been built, there's nothing you can do to change its shape. And with 3 pieces of the horseshoe bolted together, they then had to try and get the outer surface, which is the one that is the precision, it's the outer surface that's taking the weight of the northern bearing. So this has to be extremely precise. Yes, there are lugs on it at the moment. Whilst they are checking that everything is right, eventually those lugs will be removed and they'll put it on an enormous milling machine in order to make this outer surface as precise as possible. Once they had got that all right, again, it was dismantled and sent over to California to be reconstructed. The southern bearing looks more like a telephone handset when you look at it like this. The southern bearing itself is there, the south pole, and the apertures at either end are to take the 2 large tubes which make the yoke of the mounting. Perhaps you can see it a little more clearly there. The south bearing is in the middle, and these 2 ends of the telephone handset, as it were, are ultimately going to contain the cylindrical tubes which make the yoke mounting. There's the 2 tubes. The telescope is going to sit in between those 2, so these provide the structure. South bearing here, the horseshoe is going to go on this end. You can see the scale from the fact that a person is standing up inside these cylindrical yoke mounts. They are going to contain ultimately motors and other instrumentation to make the telescope actually move. All of those things were shipped across to California and then taking up the road. Remember the road, the south grade? You've got a few miles there to wind your way up, As far as I know, nothing ever fell off the road. It was quite an achievement to get all of those tons of metal up there. This is part of the horseshoe by the looks of it going up. And generally speaking, they needed 3 trucks, 2 to pull and 1 to push. Notice the name of the company, Hazard and Sons. Yeah. As far as I know, it was slow, but they never failed to achieve the goal of getting all of the bits up to the top, the bits of the telescope, ultimately the mirror, and all of the steel work for the observatory buildings themselves. Once it arrived, each of the bits of the telescope came into the observatory. They came in at ground level and then came up through the observatory floor, and then they could start putting it all back together again like a huge Lego model. So here's part of the horseshoe coming in. It looks like part of the south yoke is down the bottom, and it looks like the truss of the telescope itself is sitting there waiting to be put together. As each bit arrived, it was starting to put together. So again, the yoke is very clear, and you can see that they're starting to put together the telescope. South bearing at this end, huge horseshoe at the north end of the telescope. As it started to take shape, you again get an idea of the scale. You also remind yourself that back in the 1930s, health and safety wasn't quite what it is today. So there's no need for harnesses, no need for a hard hat. All you do is clamber all over the rig as you need to. So here somebody is checking out the prime focus cage, the cage where an astronomer might sit if they wanted to do some photography. Okay, at least this guy has got a hat. It's a fedora, not a hard hat, but it's getting there. So again, you can get an idea of the scale of the telescope, the fact that it's large enough to actually hold a person. You want to be able to move the telescope accurately to any part of the sky. So here's some engineers. I assume they're engineers because they've got the sleeves rolled up. These engineers are actually checking that can we actually move the telescope to whichever part of sky we want, and how far down can we get pointing to the southern horizon. They are never actually going to want to point at the southern horizon because San Diego is over there, but at least let's check that it does actually move as intended. So here they're just checking that it moves smoothly, accurately, and reaches the designed limits to how it points at the sky. If the telescope weighs 125 tons and the horseshoe mount weighs, with the telescope on board, about 500 tons, how do you move something with a precision of arc-second? Remember, we're talking a tiny, tiny fraction of a degree. How do you get the precision to move 500 tons with that precision? Well, part of it is making sure that you grind the gears that are necessary. A motor drives a gear train. This is the final gear that drives the right ascension. The right ascension is the polar axis. Right ascension is the name astronomers give to it. So this is the one that's going to move the telescope to a particular point of sky and then track as the Earth rotates. It's going to track and make sure you're pointing exactly at the object that you're interested in, to the sort of accuracy that we need. Again, you get an idea of scale from the fact that somebody with a hat is pointing his head through the middle there. So how do you go about grinding the teeth on a gear wheel like this? It took almost as long, not quite as long, to grind the teeth on these gears as it did to make the mirror. Because again, you need very high precision. If you want to be able to point 500 tons to an accuracy of less than 1,000th of a degree, you need to make sure your gear teeth are very accurately ground and ultimately polished. So here they are grinding and polishing on this grinding and polishing machine. And you can ask yourself, well, how do they know when they've got that right? How do you know when your teeth are accurate enough to pass muster? Well, you get an expert, who's usually a man with a pipe, to run his finger over each and every gear tooth. And you can tell from the fingerprints on the individual, you can tell if there's any imperfections on each of the teeth. And that is one of the best ways to make sure that you've ground it down to the precision you need. Then you have a worm wheel which engages with the worm itself. How big a motor do you need to turn 500 tons of telescope to a point in the sky that you need? Well, you might think that you need an enormous motor to do that, but actually you can see that the size of the motor is, well, actually not that large. If you make the telescope and its mounting precise and friction-free, then you only need the tiniest of motors to actually move it. It's reputed that once the telescope was built, they disengaged the motors, made sure it was reasonably well balanced, disengaged the motors, and then took an empty milk bottle and placed it on the telescope, and the telescope turned. It was so beautifully balanced, you needed only the smallest forces to get it to move. So I'm not going to talk through all of the drawings by Russell Porter. He made these drawings between late 30s and 1940. I'll just show a couple of them, and others are on the table at the side there if you want to have a closer look. But the precision with which Russell Porter was able to sketch out what's going on and what's going on where you can't see what's going on, this idea of a cutaway to show you how the axis works, how the gear wheels engage, the motor drive, the motors themselves at the bottom there. They even designed a analog computer. Remember, of course, no digital computers in these days. They designed an analog computer, which is basically just gears and cams, to take into account the fact that when a telescope points to a particular patch of sky, if it's looking through a little more air, then some of the starlight will get refracted by the air and the star won't be quite where you expect it to be. And this even could take into account those tiny variations in the position of a star due to a refraction through the Earth's atmosphere. And the analog computers built into this were capable of doing that. Inside one of the yokes, there's the telescope itself in the top right. This is one of the large cylindrical yokes that are supporting it. Inside is the motor that gives you the declination, the north-south rather than the east-west motion. So it's not to do with the Earth turning, it's purely a question of which part of the sky do you want to look at. So there's a large declination gear wheel, and again, motors that drive that are inside the yoke mounting itself. There's a view into the prime focus cage, so we're looking into the telescope, big mirror in the background, and an astronomer sitting in the prime focus cage there. That's how the astronomers get in and out of the cage. The telescope is tilted such that the astronomers can basically go along this little gantry and climb in, and then the telescope points to the chunk of sky, at which point the astronomer is trapped inside until the telescope comes back to let him out onto the gantry. That's what it might look like inside. Again, one of Russell Porter's drawings of an astronomer. Okay, I'm not sure why they're wearing a suit. I'm sure they'll be wearing something a little more appropriate, but that gives you an idea of how the astronomer might be sitting at this so-called pedestal inside the prime focus cage and looking at a photographic plate here, trying to make sure that the telescope is pointing at the right direction, little eyepiece there, such that the image that they want is then hitting this photographic plate at the top. It might be necessary, depending on the night, depending on what's going on, to make tiny adjustments to the position of the telescope. The astronomer has access to a paddle which allows him to control the positioning of the telescope throughout the night. So it looks like we're just about done. Everybody thinks that everything is ready. It looks like the observatory is ready. It looks like the telescope is ready. The mirror is just about being finished. Certainly the tube and the mount are complete, and the mirror is within a few millionths of an inch to the correct shape. So everybody thinks, well, we're just about there. Well, they were just about there, but then there was an unexpected delay. And the unexpected delay was because we've reached 1941. And so at this point, America joined the Second World War, which meant all of the optical shops and the machine shops were then moved over to the war effort, and everything was effectively mothballed for the next 4 to 5 years. That's why it took even longer than intended to grind the mirror, because the mirror grinding, the mirror polishing, was interrupted by the war. 1945, everything comes out of mothballs, and they go back to trying to make sure that the mirror is finished. Perhaps you can now see that the mirror has a dish shape to it, as we've now taken a few tons of glass out and it's almost the right shape. Notice also the 21 men seem to have been joined by a few women as well, so now they're getting equality in there. But there's only so much testing you can do in the laboratory. You can test to make sure that your mirror is focusing as close as you can to perfection, but the only real test is to get it out there on a dark night and photograph a star, or at least look at a star to see whether or not the star is perfectly focused. So at this point in 1947, after the war, they packaged up the mirror, sent it up the mountain on that ridiculous grade, and got it into the observatory. And by 1948, they were ready for the dedication ceremony. You can see the size of the observatory from the number of visitors they had laid out on the observatory floor there. For this dedication ceremony, there were something like 1,000 people present. And this is the point at which they named the 200-inch telescope. And it was named in memory of George Hale, who unfortunately had died a few years earlier. So he never actually saw it to completion. In the background, there's a tank there. That's the tank in which you put the mirror in order to evaporate a thin film of aluminium to give you your reflecting surface. When it arrived, the mirror was uncoated, so this is just the bare glass surface, and they wanted to check whether or not it focused correctly. So they put it onto the bottom of the telescope and then looked at night at a chunk of sky, looked at a star, and used a particular mask that allowed them to tell whether any part of the mirror surface was too high or too low. Were there any bumps there that needed to be polished down? And they were marked with these little bits of tape. This is too high, this is too high, that's too high. And then the master polisher the next day would basically say, right, okay, we need to polish those down a little bit. The final polishing got down to not even a machine. It was literally just a little bit of jeweler's rouge on his thumb, and a gentle wipe would take the last millionth of an inch off. And eventually all of these bumps would be as close to zero as they could get. Just to give you an idea, because it's difficult to visualize a millionth of an inch. If you imagine this mirror, if it was the size of the Earth, then these bumps would be that sort of size. Something over the size of the Earth, the bumps would only be measured in centimeters, only a few inches or so in size. And eventually this guy got it to the point where all of these bumps were declared as, this is as close as I can get to a perfect figure. So now we can actually go for real. We can coat this with aluminium to give us our reflective surface, and we will be ready to go. It was a process. It took obviously quite a few nights. You would try and get it right, put it back in the telescope, check a star. If it still wasn't right, you would take it out, polish it again, put it back, check a star. I'm not sure how many times they did that before it was declared as finished. When it comes to operating the 200-inch telescope, what is now the Hale telescope, you can again see an astronomer. There's the drawing of Russell Porter showing you it in section. That's what it looked like in practice. The gantry here is how the astronomer gained access, and here we have an astronomer inside. It was actually used by Edwin Hubble, who had decided some years earlier that it looks like the universe is expanding, and hopefully this telescope will allow us to get a better understanding of how the universe is expanding. Here's Edwin Hubble using this telescope, very keen to get his observing time. Having spent quite a lot of time on the 100-inch telescope, he was keen on using the 200-inch telescope to get even fainter galaxies. I'm sure they appreciated the fact that there was a war surplus of flying suits, heated flying suits, because remember, it gets very cold in the prime focus cage there. You're exposed to the elements. You're there for probably quite a few hours, taking your long exposure images on your photographic plate. So I'm sure that they were keen to have these flying suits. Here we see how it might operate. I'm not sure why we've gone from a suit to a lumberjack outfit, but okay, fair enough. So here, the astronomer is going to show you that you put the photographic plate holder in position at the top of the pedestal. You're then ready for the photographic plate itself. No, that's the back. Put it away. There's the photographic plate in the bottom left there. That's it, yeah. In the dark, you would take out the photographic plate and place that in the plate holder. Then you would put the back on. Yeah, he's got it now. Yeah, then you put the back on and you place that and make sure it's firmly in place to make sure that the plate is exactly at the focus of the telescope. You're then essentially ready. You want to make sure the telescope is pointing in the direction you want. So a little eyepiece on the side allows you to pick a star, which you can then watch as the night goes on, as the hours pass. You can make sure that that star is being tracked accurately so that you know your photographic plate is going to come out nice and sharp. Before you start the exposure, you make sure you've got your provisions. Sandwiches, yeah, peanut butter, that's fine, yeah, okay. So now you can start the exposure, and then you double check everything is okay in the eyepiece. And then for the next few hours, possibly, as the light is hitting the photographic plate, you watch your guide star and make sure the telescope is tracking exactly as it should. And if there's anything wrong, you can always make minor adjustments with a little paddle. So that brings us back to the late 40s and ultimately to the early 50s when this particular image was taken. I didn't see this in the 50s. I didn't see this image until sometime in the 1970s. But basically, this was one of the very earliest images taken by the 200-inch or the Hale telescope. And that brings me, my personal journey, round full circle. If you want to keep using a telescope 77 years later, you've got to clean the mirror every once in a while, especially if you're in California, not the cleanest of environments. So every once in a while, they take the mirror out and they give it a damn good cleaning. Literally, they get some soap solution to actually get the worst of the grime off. Once they've got that off, they then apply a small amount of rather weak acid to actually remove the silvering or the aluminium that's on the cover there. Now we can actually see again the virgin glass, which is given another clean to make sure that we've got all of the California pollution off it. And once the surface of the glass is clean, well, that's now ready to go back into the vacuum chamber to be recoated with a very thin, and by thin I mean not that many atoms, maybe a few tens of nanometers of aluminium to give it the reflective coating. Again, you can see very clearly the shapes of the cores on the underneath. It looks like you're almost looking at the top. You're looking through the clean surface at the cores underneath, which are simply rough and are showing up in reverse, as it were. Again, the hexagonal ones are simply air gaps, and the round ones are ultimately where the mirror is going to be supported in order to make sure that it's not going to distort as it points to different parts of the sky. So that's what the Hale telescope looks like today, 77 years later. It has a new lick of paint every once in a while. They clean the mirror every couple of years or so, and it is still in use. It is not the world's largest telescope anymore, but it is still in use and still has a role to play in cutting-edge astronomy. So I've told you a little bit about George Hale, about building the 200-inch telescope and how it's still in use 77 years later. I got a lot of information from the Caltech archives. Caltech are responsible for Palomar Mountain Observatory, and I got a lot of very nice information, including those videos from the Corning Museum of Glass showing you how the mirror was made back in the 1930s. I also picked up a lot of material from these publications, some of which gave us the drawings that I'm showing on the front bench there, especially these publications by Russell Porter, Giants of Palomar, and Photographic Giants of Palomar. This book got me interested in the first place. It's a book written in the 1930s explaining why and how the 200-inch telescope ultimately came to be. So the Hale telescope was the largest telescope in the world when I was born. It was the largest telescope in the world for all of my schooling. It was the largest telescope in the world for a fair chunk of my adult life. It wasn't actually superseded. Remember, it was designed in the 30s. It wasn't actually superseded as the largest telescope in the world until the 1990s. So most scientific instruments don't live and perform for half a century. It is quite exceptional that you have something that was ahead of its time in that sense, if you'll excuse the cliche, and was still producing useful work more than half a century later. And even 77 years later, it is still producing useful output, despite the fact it's not actually the largest in the world anymore. But the fact that it's been producing useful work for nearly 3/4 of a century is testament to the people who designed it, the people who built it, the engineers who make sure it operates, and above all, the person who had the vision and the drive to bring it all together, George Ellery Hale. Thank you very much.
Thank you very much. Thank you.